Good afternoon everyone. I am Chanda Devnath, the TA of this course, the study guide in organic retrosynthesis problem solving approach. So in these classes I usually discuss about some organic reactions which may help you to plan a retrosynthesis of any compound. So as I have already mentioned that in these classes I am trying to first few classes I am trying to cover up all the different type of important name reactions which may give you an idea or to plan a retrosynthesis of any compound. So let's start. So we are discussing about some important name reactions. In the last classes, last class I was discussing about Aldol reactions and Michael and followed by Mitsunobu reaction. Robinson annulation. I just introduced that one. So today I will complete that. Then we will go to a new type of name reactions and some others. So this we have discussed in the last class, what is aldol reaction and Michael addition. So the combination of these two reactions is called Robinson annulation. So Robinson annulation is a useful reaction for the formation of six-membered rings in a polycyclic compounds. So this Robinson annulation is one of the important reaction to synthesize any steroid kind of compound because it's directly give us a six-membered ring. So to plan a retrosynthesis of any compound, this is one of the important reaction. So it combines two reactions, one is Michael, then after that aldol reaction. So if you see into the mechanism, there is a ketone and this alpha beta unsaturated compound get combined to give us this steroid moiety. So how this happens? First, this alpha hydrogen get taken up by a base, and this through enol formation it will attack to this alpha beta unsaturated beta carbon of this alpha beta unsaturated ketone and form this intermediate. After that the base will take another proton from this methyl like this way and from this annular intermediate again, and after that it will attack to this annular intermediate attack to this carbonyl compound. So this is the aldol reaction. So first reaction is the Michael reaction. Here it is the Michael reaction because it is attacking to the beta carbon. Whenever the nucleophile is attacking to the beta carbon, that is called Michael addition. That is called Michael addition. Is called Michael addition, and in this case this enolate carbon is attacking to this carbonyl compound to form a new carbon-carbon bond. So this is similar to the aldol reaction, and after elimination of one molecule of water, this is generation of double bond, and after elimination of what, there is generation of double bond, it will give this as our product. Okay, so this is a Michael followed by aldol, which is called a Robinson annulation. So this is one of the important one. So next here they have given this cyclic ketone and this alpha beta unsaturated compound and asked for the product. So let's go step by step. So here acid is given. So obviously the aldol first the enol will form. So in presence of base, usually there is a H here and there is H here. Whenever the reaction is base catalyzed, whenever any reaction is base catalyzed, it will take up the more acidic proton. It will take the more acidic proton. But in case of acid catalyzed reaction, there is no question of acidic proton take up. So here In case of acid catalyzed reaction, how the mechanism goes, in case of base catalyzed reaction, it will take up a proton from this alpha carbon and this negative charge goes here and this opens up. But in case of base catalyzed reaction, first this carbonyl oxygen get protonated. After that, between these two alpha hydrogen, one of them undergoes a deprotonation to neutralize this oxygen atom. So one probability is deprotonation from this center, one probability is deprotonation from this center. Now if we think this proton is getting deprotonated from this carbon, so the enolate will be like this. Okay, but if the proton is eliminated from this carbon, then the enolate will be so then enolate will be like this. So among these two, which one is more stable double bond? Obviously this one, because this is more stabilized double bond because of presence of more hyperconjugative hydrogen. This is more substituted double bond, because of that this double bond is more stable. So which one is our expected intermediate will be this one. Okay, so always think about, always you have to look which reagents has been given. If the reaction is base catalyzed, always take up the more acidic proton, that is this one, it is the more acidic proton, and the enolate will be like this. But if the reaction is acid catalyzed, the double bond will be placed where the double bond is more stabilized. So in that case the proton will be taken up from the less acidic one. Okay, like this. So what will be the next step? Next step, it will attack to this alpha beta unsaturated ketone, and it will form still there will be a minus H plus from here, and there will be a plus H plus to this alpha carbon, to this alpha carbon. After that, still acid is remaining. So there are two alpha hydrogen, one is here, another three is here. Now which one will be taken up? Now if we take a alpha hydrogen from at this place, and if it coordinate with this carbon, so it will form a four member ring. If it will form a four member ring, you are getting it right. If you are taking proton from at this place, there will be negative charge here. What happens in aldol reaction? It will attack to this place and it will open up. So the formation of the bond will be from here. So it is a four member ring. So we know that four member rings are not stable. But if protons are taken from here and this will attack to this center, then the formation will be a 6-member ring. The formation will be a 6-member ring. So obviously this attack is more favorable than that of, okay, because here the 4-member ring will form. So in this case, this instead of acid condition, the more acidic proton will be taken up. Understood? You have to consider all the factor, because usually in case of acid catalyzed reaction we usually take a proton which gives a more stable enolate. But in this case, if you take a proton from here, the newly formed bond will give us a 4-member ring. So that's why we are taking a proton from here. So it will attack to this place and it will form, I am not drawing the enolate again, so it will form a 6-member ring. There is a methyl here and there is a OH. After that, there is a H still available. If we eliminate one molecule of water, there will be generation of a double bond here. Okay. Now what will happen in this case? Suppose we are giving base. We are giving a base. What will happen in this case? So obviously, as base catalyzed, so if you take a proton from here and it attacks to this place, it will give us a 4-member ring. But if you take a proton from here and it would attack at this place, it will give a 6-member ring. So obviously it will take a proton from at this place and it will attack to this carbonyl carbon. Okay. So we generate a double bond here. Okay. So this is our product. Next topic is Apple reaction. We know substitution reaction, that is we have read in our class 2 I think. So substitution reaction, what is substitution reaction? When a nucleophile comes and attack to a carbon center and substitute the group from at that place, that is called substitution reaction. Now leaving group leaves from the system through incoming of a nucleophile. Now suppose your leaving group is not a good leaving group. Suppose your leaving group is less prone to leave the system. In that case, what you will do? Suppose you have such a kind of substrate. You have some kind of substrate and the leaving group attached to it is not a good leaving group. It's not a good, so that means good leaving group not means bad leaving group means the bond between the leaving group and the carbon atom is highly strong. The bond between the leaving group and the carbon atom is strong. So this is less prone to break. These bonds are less prone to break. In that case, what we will do? In that case, we do perform in such kind of reaction so that this bad leaving group after some reaction becomes a new kind of leaving group where it acts as a good leaving group, means the bond between this carbon and this leaving group is weaker than the previous one. This bond becomes weaker than the previous one. So this is one of the example of this one is Apple reaction. So this is a reaction of triphenyl phosphine and tetrahalomethane with alcohol. This type of reactions are applied when in your SIP system there is a OH group and you want to substitute that one. We know that OH carbon oxygen bond is one strong bond, and OH group is a bad leaving group, because suppose this type of substrate is given. When you eliminate this OH group, it get eliminated from the system as a OH minus. Negative on a oxygen has no such d orbital, vacant d orbital, to accommodate this extra negative charge. It is a very small atom, and as it is charged species, this leaving group is not stable after, is not that much stable. Because of that, this carbon oxygen bond is less prone to breaks, because it is a bad leaving group. It's not labile enough to leave, to get broken by any kind of nucleophile. In that case, we perform this Appel reaction, where this, in presence of PPH3 and tetrahalomethane, this oxygen OH transform into such kind of a group which get easily eliminated by incoming nucleophile. So this is the mechanism where first this PPH3, will attack to this tetrabromomethan. In that, one bromine will eliminated from the it will attack to this bromine, and it will get eliminated from the system, from this species. After this, and this negative charge will take a proton from this, hydrogen, from this alcohol. After that, this O minus will attack to this phosphorus. As we know, oxygen phosphorus bond is one of the strongest bond, so it will attack to the oxygen phosphorus, and bromine will eliminate it, and it will form this type of intermediate. After that, when the nucleophile will attack to this center, this species will get eliminated, and we get as our substituted product. And the driving force of the reaction is formation of oxygen phosphorus bond, because oxygen phosphorus bond is one of the strongest bond in nature. So as a similar type of reaction is Mitsunobu reaction. In this case, we also substitute a OH group, but instead of PPH3 and a tetrabromomethane, we are using diethyl azo dicarboxylate instead of the tetrabromomethane, because in tetrabromomethane there is elimination of bromine atom. So, and we know that bromines are not that much safe. So in that, as a substitute, we came up with the idea, scientists came up with the idea that is called diethyl azo dicarboxylate. So it allows the conversion of primary and secondary alcohol to ester, phenyl ether, thiether, and various other compounds. The nucleophile employed should be acidic, and since one of the reagent must be deprotonated during the course of the reaction. So if you see these examples, so if you see the mechanism, first the PPH3 will attack to this diethyl azo dicarboxylate, same as like tetramethane in tetrabromomethane. Then this negative charge will take a proton from the nucleophile, and it will activate our nucleophile. After that, this alcohol proton will attack to this phosphorus, similar to the Appel reaction, and will eliminate this from the system. And again, this nucleophile, the newly generated nucleophile, will approach to this oxy atom, forming, then this H minus will shift here and eliminate it. Then after that, this activated nucleophile, this activated nucleophile the activated nucleophile will attack from the opposite plane of this leaving group, and it will eliminate oxygen from the system. Okay, that's similar to Appel reaction. The point to be noted in this type of Appel reaction and Mitsunobu reaction is that if you are taking a chiral compound, suppose if you are taking a compound having 4 different groups along around the carbon center, so it is like a chiral compound. In that case, whichever plane the leaving group holds, the nucleophile will approach from always from the opposite plane. So this is a SN2 type of substitution. It's a SN2 type of substitution. So whatever will be the stereochemistry of our OH, that is our leaving group, the newly generated product with a new group substituting the OH group will be just in the opposite plane of the alcohol. So you can notice here the OH group is above the plane, whereas the acid group is below the plane. The OH group is above the plane, the newly entered N3 minus the N3 group is below the plane. So what will be the product in this case, in this reaction? This is from one of the research paper. I haven't mentioned it, but one of the research papers. So what will be the product in this case? So instead of PPS3, they have used PCY3, and instead of diethyl azodicarboxyl, they just use diisopropyl azodicarboxyl. This is the difference. Just instead of PPS3, they have used different phosphine, and instead of azodicarboxyl, they have just used diisopropyl. Mechanism will be everything will be same. So just think what will be the product. You can notice that no nucleophile has been given. So obviously there is something already in the system which will act as a nucleophile. So among these two OH, for the first attack is the oxygen is attack first. This PCY3 and isopropyl azodicarboxylate form intermediate species, that is like this one, intermediate species that will react with our new leaving group, that is OH. So between these two OH, which one is more nucleophilic? Because first attack is the OH is attacking to that intermediate species, that is into the phosphine, into the phosphine. The first attack is this OH is attacking to this phosphorus center. So among these two OH, which one is more nucleophilic? So here there are two carbon bond, and here in this case one carbon bond. So obviously this oxygen has more electron density on itself. So this oxygen will will attack to that phosphorus. I'm just noting is the phosphorus species. After that it will form a good leaving group, and then this intramolecular attack of this nucleophile to this carbon center will eliminate the oxygen from the sheets. Now in this case this oxygen is already below the plane, so this planar OH will approach from to substitute this OH group, will approach from the above the plane, will approach from the above the plane. So the newly generated epoxide stereochemistry will be kind of like this. Now in this case you can see instead of this tetrachloromethane, they have used this type of nucleophile. This can also act as a chlorinating source because it will attack to this one of the chlorine atom and will eliminate this species. And after that the Cl will attack here again and it will give us this as our product. Now what will happen in this case? If you perform the same reaction in case of epoxide, what will happen? So suppose, so in this case also they have given this catalyst, this phosphorus catalyst. So this oxygen will, this phosphorus catalyst will react with this chlorinated species, generating a positively charged intermediate. Then this oxygen will attack to that phosphorus species. It will attack to this phosphorus species. If I go, let me go step by step. I think I am doing too much step jump. So this will attack so this phosphorus, just similar to the apple reaction, it will attack to one of the chlorine atom and it will open up. Chlorine can take up add up because it has a vacant d orbital. So after that it will form after that this epoxide oxygen will attack to this phosphorus center and removes one chlorine from the system. Generating this type of species. I'm not drawing it properly. You have understood, right? A similar type of species. After that, this chlorine atom which has been eliminated, this is still in the system. So that chlorine atom will attack here and it will open up. So it will give us this as our product. Now this oxygen is still coordinated with the phosphorus. Then another molecule of chlorine atom will attack. And give us a dichlorinated compound. Okay, I hope it is clear. Let's go to the next topic. So, before that, sorry, there is a mistake. Everything will be just still be not correct. So what will be the product of this reaction? So yeah, obviously this OH group will be eliminated by this acid group. So now the OH group is above the plane. So the newly come and newly generated acid will come from the below the plane. So it will come from the below the plane. Okay. Next is here. So just see the whenever you are seeing this DAD and PPH3, always think about Mitsunobu reaction. And if it's a Mitsunobu reaction, wherever plane is the OH is, the newly come nucleophile will be just opposite to that. So here it is above the plane. So the newly formed carbon oxygen bond by this acid will form will be below the plane. Okay. Next is this one. So if this react with this OH group and makes up it's a good living group, then in that case this OH will attack here and it will be eliminated. Forming this as our product. Okay, let's go to the next question. This is one of the question from NET, I think previous year NET question. So what will be the product? In the first step they have given PPH3, DAD and 4-nitrobenzoic acid. In the second step they have given a base and methanol. What will be the product? So whenever I said if there is a OH group and this reagent combination is given, this is a Mitsunobu reaction, and wherever the OH is, the incoming nucleophile will be just opposite to that. So as the OH group is below the plane, so this 4-nitrobenzoic acid will be above the plane. So the product is, after the step 1, the product is like this, 4-nitrobenzoic acid. I'm just drawing at a pH. Next step, next if you add K2CO3, what will happen? And methanol, this methanol and K2CO3 will form potassium methoxide, and this potassium methoxide will attack to this ester, performing a trans esterification, and the product will be option B. Okay, next topic we'll discuss, that is coupling reaction. So in organic chemistry, a coupling reaction is a type of reaction in which two reactant molecules are bonded together. Such reactions often require the aid of a metal catalyst. in one of the important reaction type, a main group organometallic compound of type Rm will combine with Rx, formation of a newly carbon-carbon bond that is called R dash. The most common type of coupling reaction is cross-coupling reaction. Broadly speaking, there are two types of coupling reaction. One is homocoupling, another is heterocoupling. Homocoupling means if the two coupling partners are identical, these are called homocoupling. And if the two coupling partners are not identical, then that is called heterocoupling. So there are different type of coupling reactions. If you see the examples of like Ullmann, Urch, Benjoin, there are many more. I just mentioned three to give you an idea. There are many more. So homocoupling means if two similar type of component get coupled with each other, it is called homocoupling. And heterocoupling means if two different type of component get combined with each other, that is called heterocoupling. So there are many examples of that one. We'll go one by one. So first, Hake reaction. So in case of Hake coupling, actually I haven't discussed about all the couplings. I just directly jumped into the questions because I hope if you want to know about the coupling, you can check my previous classes or of previous videos also. In that case, you'll get this type of couplings details, or you can study from book Claydon. Organometallics chapter is one of you can go through that chapter. Claydon organometallics. There is a chapter in Claydon. If we go into that, you will get most of the all the couplings reaction is there. For basic idea, that is a good book. So it's Hake coupling when uh, when a Rx is carbon halogen bond and a CH bond get coupled with each other in presence of palladium, that is called Hake coupling. Suzuki is when a Rx and carbon boron bond get coupled with each other, that is called Suzuki coupling. Like this one, there is many more. So let's not waste. We are just let's solve the questions. During solving the question, we'll get an idea about the mechanisms also. If you have any, just take a session, just go and read the coupling reactions from Claydon. If you have any doubt, I will try to discuss the mechanism about all the coupling reaction in the next class. So this is one of the questions from previous year NET. In all the NET examination, there is at least one question from this type of coupling reaction. So you can understand how much important is this. In every NET examination, at least one question will be from this topic. And so, and due to this broad application of this type of reaction, coupling reaction, to form a new carbon-carbon bond and to plan a retrosynthesis of a compound, this is a very important reaction. So in this case, they have given first step, they have given this PPS3 and DAD and 2-iodophenol. So from the reagents and the substrate, you can get an idea that this is a Mitsunobu reaction. This is a Mitsunobu reaction. Whenever there is alcohol and this combination is given, always think about Mitsunobu reaction. Then they got A, and in that case they have given, so this is a new reagents for you. I will try to discuss about this one in next class. And they got B. So it will be the A and B. So A is simple for you guys because you already solved many of them. As the OH is already above the plane, so the incoming nucleophile, that is 2-iodophenol, will be at the below the plane. Will be at the below the plane. So these two above the plane questions are already cut. So the correct option will be between A and B. Now in the next step, they have added this Bu2SNH. This Bu2SNH will take a iodine from here and generate a radical at this place, and this radical will coordinate with this double bond and form this cyclase compound. Now just to imagine this in 3D, I'm just rotating this one and drawing in a different way, just for your understanding. So there is a radical here. This radical here. Now this radical will combine with this carbon center. So there will be 1, 2, 3, 4. So there is generation of 5 member ring. So it will combine with this alkene center through addition reaction and it will form a 5 member ring. Now the question is, this will approach from the above the plane or below the plane? That is the question, because in the one option our methyl group is above the plane, one option the methyl group is below the plane. Means in the one option this radical is approaching from the below the plane, keeping this methyl above, and one is approaching from the above the plane, keeping the methyl below. So obviously this, you have to, for that one you have to consider the stereochemistry of this carbon oxygen bond. Now as this is below the plane, so if it is a like a plane and it is below the plane, means this phenyl group is already below the plane. So if it wants to approach to this carbon, it have to approach from the below the plane. Just imagine in 3D something, suppose there is a rope and rope is attached below the plane, rope is attached just below the plane. Now if you have uh, knotted some stone or anything, rock, to that rope, so that will approach from the below the plane. So obviously this radical will approach from the below the plane, keeping this methyl to the above. So the correct option is option A. Okay, let's go to the next one. The major product form in the following transformation. This is one of the question from NET in the recent years, in maybe in 2025 June, I think. So what is the major product form in this transformation? So this is the example of Heck reaction. So first this palladium and this halide will form RPDX complex. After that it undergoes a 1,2 addition across the double bond. Now as the phenyl group is already attached below the plane, so this is already attached below the plane. So this total complex will approach from the above the plane. So PD I will attach here and R will be attached here. Now as there is no seen hydrogen available at this carbon, but there is a proton here, which is at the same plane. So it will undergo the 1 to elimination. Forming a double bond here. So there will be phenyl here. And the naphthyl. So the correct option is option 1. No, sorry. And there is, I just drawn it wrong. Okay. Let's go to the next one. What will be the major product A and B? This is an example of Suzuki reaction. Whenever there is a boron and cross coupling reaction, it is called a Suzuki reaction. So what will happen in this case? So first there is a carbon halogen bond, so it will form a, with palladium it will form a PDI. Palladium will insert to this carbon halogen bond, forming a PDX complex. After that, this carbon center will combine with this carbon center, forming this as our product. So A and B are already cut. So the correct option will be between C or D. It will form this. After that, in next step, if you add H3O plus, what will happen? In presence of H3O plus, this OET will be protonated. This OET will be protonated. Becomes a good living group, and this in nucleophile will attack here, deprotonate from the system, and giving this indole ring as our product. Okay. Let's go to the next one. What is the major products A and B in the following reaction? From boron you can get ideas how this is also a Suzuki reaction. I just give 1 second to 5 seconds, just get an idea. What will be the product? Just think. So what will be the product? So first it will undergo the hydroboration. It will undergo a hydroboration reaction. it's a catechol boron. This is a catechol boron type of product. So it will undergoes a hydroboration. So obviously it will be a syn hydroboration. So product will be between A or B, C and D are cut because hydroborations are always seen in manner. So here the boron is attached in one side, hydrogen is attached in one side. In the next step they are giving this iodide, alkene iodide, so it is a high coupling type of reaction. Now what will be the product? Now you have to just draw it as a R. Boron is attached here. Now in the next step you have I. So you have to draw the product keeping both the alkene stereochemistry intact. You have to draw the product keeping both the alkene stereochemistry intact because it is a coupling reaction. So there is no probability of rotation of these double bonds. There is no, because that we know that double bonds are highly stable and you can't break those bond and you can't rotate that one. So you can't, there is no probability of rotating this double bond. So you have to plan a product keeping the stereochemistry of this double bond same. So the product will be like this. So it's a trans double bond. So here it will be a Z and it will be a E. So the correct one will be option B. Correct option is option B. Okay. So you have to notice that in case of coupling reaction there is no probability of changing the stereochemistry of the double bond. So you have to draw the product in such a way that the stereochemistry double bond is retained, and also while denoting the product in the options always go to this naming so that there is no because you may have done some mistake if you just tick that one, okay, this is two trans double bonds, so you are just connect. So you always go through like easy, so it will give a better idea of the correct answer. In the following reaction sequence, what is the structure of A and B respectively? In the following reaction sequence, what will be the structure of A and B respectively? So first one is I2PPH3 and imidazole. So from that one you get an idea, it is a apple reaction. This is a apple reaction because halogen is given and as well as a PPH3 is given. So it is a apple reaction. So obviously this OH will be substituted with this iodine. So the correct option will be between A or B. So B, C and D are already cut. Now in the next step they have added zinc, palladium and copper iodide. So there will be a coupling reaction. Now from, in this case it is clear, okay, this iodine carbon iodine bond will be broken to take part in a coupling reaction. But in case of this substrate we have a chlorine and a bromine. Between chlorine and bromine which bond will be broken? Because both are halogen carbon halogen bond, which will be broken? Obviously the carbon bromine bond, because carbon bromine bond is weaker than that of carbon chlorine bond, because carbon bromine bond is between 2p 4p, the overlap is between 2p 4p, but whereas in case of carbon chloride it is 2p 3p. So due to size match the bonding is stronger in case of carbon chlorine. So this bond is stronger than that of carbon bromine, so this will be broken easily and will form a coupling product, this one. So the correct option is option A. Understood? First one is apple reaction and second one is cup. So you can see that in case of in NET gate examination, there is multiple times in almost every year. In almost every year we are getting 2011, 2012, 14. So almost in every year, and I have shown one of the question in recent year also, that is in 2025. Almost in every year we get a question from coupling reaction, and it is not only that it's only based on coupling reaction. There will be one question along with that, one name reaction which is coupled with that one. So, and because of this huge application of this reaction, you can, to plan any retrosynthesis of any large molecule, we have to use this type of reaction. When we will go into the retrosynthesis of the molecule, you will see then every step almost we will get this. So first we have to find the alpha hydrogen. So this is called alpha hydrogen. So in presence of base, it will be eliminated and it will generate a negative center, negative charge here. After that, it will attack another molecule of aldehyde. And this get open up. Okay. So if you had one molecule, if you just eliminate one molecule of water from this place, it will give us the condensation product, that is a alpha beta unsaturated aldehyde. Okay. The similar thing will happen in this case also. If there is alpha hydrogen, what is alpha hydrogen? Both the centers are, both the alpha carbons are equivalent. So you can take proton from one of them. So just consider two molecule and you will get this as our product. Okay, we will get this as our product. Mechanism is similar, so I am not drawing it again. Next one, how will you plan the retrosynthesis of this compound? So obviously, as I am discussing about aldol reaction, so aldehyde reaction will be one part of them. So what will be the retrosynthesis of this compound? So we know this type of compounds can be prepared through retrosynthesis if you just cleave along this alpha carbon, alpha bond. What is the probability? what is the synthetic equivalence? As negative charge at the alpha carbons are stable, so we are keeping negative charge at this place, and as oxygen is attached to this carbon, so we are keeping positive charge at this place. So these are these two synthetic equivalent. So what are the synthon? Aldehyde, and this can be simple cyclopentanone. So the forward synthesis you can plan easily. It's a simple aldol condensation. You will just take a proton from this alpha carbon. This will attack to this aldehyde center and open up to give us this as our product. Okay. Let's go to the next question. What will be the correct answer for this reaction? So suppose this is A, B. What will be the product of this reaction? I just give 5 seconds. Just think. So simple aldol reaction will take place. There are two aldehyde center, and as they, in this case there are two ketones, so there are two alpha carbon. One is this one, another is this one. So we can take a proton from this at this place as well as at this place, and after elimination of both the proton, this carbon center can attack to this aldehyde center. So the product will be so after elimination of, there will be a wedge. Okay, so after elimination of water, as there is another alpha hydrogen is available, so this will come here. So after elimination of two molecule of waters, so the correct option will be option B. Correct option is option B. Okay. Let's go to the next question. Provide the method using aldol reaction. So this is again the simple one. We just have to break along this double bond. So and we're just breaking one bond, okay, the double bond. So what will be the synthetic equivalent? So after breaking this double bond, we are keeping a negative charge here because it is adjacent to alpha carbon, and a positive charge here. Adjacent to alpha carbon, the negative charge is always stable than that of positive charge. So we keep after the synthetic equivalent will be like this, not the opposite one. So this is our synthetic equivalent. After that, if you now to satisfy this positive charge, there should be a leaving group. There should be a leaving group. So the synthon will be kind of like this. And there is a H plus. Okay. After that, if you break this double bond again, if you break this bond also, now as OH is attached, so a positive charge at this center is will be stabilized by this OH. So we are keeping positive charge at this carbon and a negative charge on this carbon. Okay, so now it can be aldehyde, and this can be also a, so here you can see by using just simple aldol reaction we can predict the retrosynthesis of this compound. Next is provide the method using aldol reaction. So you have to provide a method using aldol reaction. Now see, there is a difference. If you just think that this is also a 2 molecular aldehyde, but it is not adjacent to the carbonyl. So this is not at the beta carbon. This is not at the this carbon-carbon bond has formed at is not at the alpha carbon. The carbon-carbon bond has formed at the beta carbon. So if you break this one, so the now in this case the synthetic equivalent will be bit different. Now if I have, as you have broken this bond, now this one is not at just is not at the alpha carbon. This is the beta carbon at, according with respect to this carbonyl atom. This is alpha. This is beta. So we know that positive charge at beta carbons are usually stable than that of the negative charge. So if you keep a positive charge here and this carbon at is at alpha carbon, so you can keep a negative charge at this place. Okay, so what will be the synthetic synthon for this two? So simple H plus, if you add a H plus we can get this 1,2 diketone type of compound. Next, to satisfy this positive charge, what will be the synthon for this one? If you just eliminate this H, it can be a alpha beta unsaturated ketone. So you can get an idea about the forward reaction. So this will be a Michael addition. This will be a Michael type of addition. Now to prepare this one also we can use sorry, not the, to prepare this one also you can use aldol reaction. If you break the bond at this place, so I put a CH3 here. Okay, so this is prepared through aldol reaction, and this, after that, this alpha beta unsaturated cyclopentanone get conjugated with another molecule of this diketoaldehyde, then it get this Michael addition product. Okay, let's go to the next question. What will be our A, B and C? In all the cases, LDA is given. LDA is a base. LDA just consider is a base, aluminum based base like butyl lithium or something. What will be the product A, B and C? So let's just give a hint that obviously there is a alpha hydrogen here. So it will take a alpha hydrogen from this at this place and it will form a enolate. After the formation of enolate, it will react with all the three types of electrophile. This is also electrophile. This is also electrophile aldehyde. This is acyl chloride and this is a allyl bromide. So it will react with these three types of electrophilic electrophiles. So what will be the product? I just give 2 seconds. Just try. So what will be our first step? First it will form this enolate. It will form this enolate. After that it will react one by one. Suppose in case of A, it will react with this acyl chloride. So the product will be will simple just attack and remove the chlorine atom. So the product will be this diketone type of compound. So the correct option will be this one. So these two are already cut. These two are already cut. 1 and 4 are already cut because the correct option is this for A, between A. Now let's see the B. So what will be the B? This is our A. Now if it attacks to this aldehyde, it will be simple aldol reaction. Aldol if it attacks to this, it will be a double bond here and methyl. It will be a simple aldol condensation mechanism. I hope you will get an idea because you have solved many more questions based on this. So I'm just jumping to the answer. So this will be our B. So both of them have same B. So the deciding will be option C. Sorry, the deciding will be what will be the structure of C. So if we attack to this, if this attack to this allylic bromide, it will attack to this carbon and it will eliminate this bromine from the system, giving this as our product. So the correct option is option this type of small reactions. What is the major product form in this reaction? What is the major product form in the following reaction? So they have given this alcohol and at palladium, and there is no such leaving group is given. So what will be the product? So as I have said, just go and read this organometallics chapter. In that case, along with coupling reaction, you will got a reaction that is called Suji-Trost reaction. This is a new topic I am introducing. I will discuss about this one in next class. I am just giving a brief so that you go and read. It is called Suji-Trost reaction. This is one type of reaction that is called Suji-Trost reaction. Suppose this type of compound is given, allylic bromine. So bromine is a good nucleophile. Now you are adding a palladium. So in that case, palladium will be entered to this carbon-bromine bond. After that, this palladium will coordinate with this double bond and eliminate this bromine atom, forming this pi-allyl species. This is called pi-allyl species, pi-allyl complex. After that, now both the carbon center is available for the attack of the nucleophile. So the nucleophile can attack here as well as here, giving us a substituted product. So this is called Suji-Trost reaction. Now in the next generation, this is a way this reaction was came in 90s around. So when people use this reaction is broadly applied in most of the reaction, because by this reaction you can easily incorporate any allyl group in any reaction, and allylic esters, amides, amines are highly important in case of biological compounds. But scientists face drawbacks that in this case, in this type of reaction, you always need a leaving group. You always need a leaving group to form a pi-allyl complex. So there is another scope. If you have this type of allyl complex with the allylic H here, and you add palladium and any oxidant, in that case this H get oxidized in presence of this oxidant and form a pi-allyl complex. So here, by this methodology, in absence of leaving group, we can also form a pi-allyl complex. In absence of leaving group also, we can get a pi-allyl complex. Now the nucleophile will approach to one of the center, giving us this allylated species. So here in this case, the same thing happening. Oxygen and palladium is given, and there is allylic H. So in presence of this allylic H will take up and form a pi-allyl complex here. This is one question from recent NET examination. I found it interesting, so I introduced it. So it will form a pi-allyl complex here. Next, this OH, if the OH attacks here, Then the double bond will shift at this place, and the correct option will be option 1. Okay, so the product will be like this first. Sorry, not this. I just missed one carbon, I think. Will attack to this carbon. So suppose if it then now this oxygen will attack or this carbon or this carbon. If it attacks to this carbon, there is a formation of a 5-member ring. Now from the options you can see there is no such 5-member ring. So the only probability is it attacks to this external carbon. So the correct option will be a 7-member ring. So 1, 2, there is a methyl here and 1 methyl here, and there is a palladium. No, sorry, there is a palladium because oxygen is attacking here at this place, so palladium will be in this place. You understood it? I'm just drawing it. If the oxygen is attacking to this place, suppose just so see from there, if the nucleophile approach from this plane, from this side, in that case the nucleophile will form a bond here, and this double bond and palladium will form a bond here. Then it will get eliminated, forming this type of allylic bond with the nucleophile. So the similar case will happen in this case. So palladium will be at this place. Now there is two probability, one H is here, one H is here. So one H can be eliminated from this place or this place, generating a double bond. Now if you eliminate a H from here, the generating double bond is more substituted than that of this one. So the H will be eliminated from this place, giving the correct option is option C. Correct option is option C. Okay. So this much for today's class. So in this class we have discussed about some important name reactions, where we discuss about first this Robinson annulation and solve some questions based on that, Apple reactions, Mitsunobu reaction and some questions. Then we jumped into the coupling reactions and we solved some questions previous year. So thank you everyone. We'll meet in the next class where we will solve more name reactions, and after that I will try to discuss about retrosynthesis of some important compounds. I'll take the compounds and how to plan a retrosynthesis of those then we'll do that, because it's fourth class, I think. Next class will be also dedicated to this type of important some name reactions or important reactions to plan a retrosynthesis. After that we will have three classes, and all these three classes we will discuss about some uh, important compounds and some retrosynthesis of those one. Okay, so thank you everyone, have a nice day.